The size of an atom is so minute that it makes a virus particle enormously huge in comparison. Assuming there are 1000 atoms that make up the virus particle as shown. Click the Magnify times 1000 button to visualize the size of an atom as compared to a virus particle. Looking at the animation of an atom, the electrons that are revolving around the nucleus seem to be close to the nucleus. In actual fact, the electrons are so far away from the nucleus that we are not able to show the diameter of the atom within the limits of this screen. The diameter of an atom is about 10 to the power minus 10 meters. Rutherford's scattering experiment suggested that the nucleus has a diameter of about 10 to the power minus 15 meters. If the nucleus were the size of a wheel of diameter 1 meter placed at the center of Dataran Merdeka in Kuala Lumpur, the atom would have a diameter of 100 kilometers. Click the Visualize button. Since the diameters of an atom and the nucleus are approximately 10 to the power minus 10 meters and 10 to the power minus 15 meters respectively, this means that the atom is approximately 100,000 times the size of the nucleus. Introduction to Nucleus 1. In this lesson, you will learn to describe the discovery of neutrons, to identify the symbol of a nucleus of an element, the equivalence of mass with energy, and the use of the formula E equals mc squared, the use of the units U and eV, to explain mass defect and nuclear binding energy. Transmutation is transformation of one element into another by one or a series of nuclear reactions. In 1919, Ernest Rutherford suggested that transmutation could happen when an element is bombarded with fast-moving particles. Particle accelerators have been used by scientists to carry out many nuclear reactions. New elements have been produced in the laboratory using nuclear transmutations. The animation shows changing iron into gold. Unfortunately, this is practically impossible. In 1932, James Chadwick used alpha particles from radioactive polonium to bombard a beryllium target. He noticed that a radiation of penetrating power much greater than that of alpha rays was emitted. The radiation was initially thought to be energetic gamma rays. By using the principle of conservation of energy and the principle of conservation of momentum, Sir James Chadwick discovered that the radiation consisted of neutral particles of mass about that of a proton. He named these particles neutrons. Before 1930, the nucleus was thought to consist of only protons. With the discovery of neutron by Chadwick, a clearer picture of the nucleus was formed. All nuclei except hydrogen-1 are made up of both protons and neutrons. Summary. The discovery of the neutron by Chadwick led to the suggestion that all nuclei except hydrogen-1 are made up of protons and neutrons. The nucleus of an element is represented symbolically using the above notation. Click on Z, A, and X to know what they denote. The nuclide notation of carbon-13 is shown. What is the mass number A and atomic number Z of the carbon-13 nuclide? Answer: A equals 13 and Z equals 6. Calculate the number of protons and neutrons in carbon-13 nuclide. Answer: number of protons equals 6 and number of neutrons equals 7. A nucleus is denoted by the symbol XZA, where X is the symbol for the element, Z is the atomic number equals the number of protons in a nucleus, A is the mass number equals number of nucleons equals number of protons plus number of neutrons. The Einstein's equation E equals mc squared relates mass and energy, where E is known as the rest mass energy, or the energy equivalent to the mass m, and c is the speed of light. The principle of conservation of mass energy is based on E equals mc squared. If there is any change in the rest mass, then according to E equals mc squared, there will be a release of an equivalent amount of energy. Determine the rest mass energy equivalent to 1 kilogram in 1 joule, 2 mega electron volt. Click the Part 1 button and the Part 2 button to see the solution. Summary. The Einstein's equation E equals mc squared relates mass and energy. The mass spectrometer is used to determine the mass of ions. The mass of an ion is directly proportional to the radius r of its path in the spectrometer. This will be discussed in more detail in the next lesson. From the definition of unified atomic mass unit and that 1 mole of carbon-12 has mass of 12 grams, the mass in kilograms equivalent to 1 U can be calculated. Click the calculation button. A change in the rest mass results in a release of energy which can be calculated from E equals mc squared. Click the conversion button to calculate the energy equivalent to 1 atomic mass unit U. Summary. 1 unified atomic mass U equals 1.66 times 10 to the power minus 27 kilogram. A mass of 1 U is equivalent to energy of 931 mega electron volts. Drag the helium nucleus to the left electronic balance to measure its mass. Now drag the constituent nucleons of a helium nucleus, 2 protons and 2 neutrons, to the right electronic balance to measure the total mass. Notice that the mass of the helium nucleus is less than the total mass of its constituents. This difference in mass is called the mass defect. Click the Mass Defect button. It follows that in order to separate a helium nucleus into its individual nucleons, an amount of energy equivalent to the mass defect must be supplied. This energy is known as the binding energy of the nucleus. Click the Binding Energy button. Calculate the binding energy of an iron 56 nucleus. Click the Answer button for the solution. Summary. Mass defect of a nucleus equals total mass of constituent nucleons minus mass of nucleus. Binding energy of a nucleus is the energy required to completely separate its constituent nucleons. Binding energy of a nucleus is the energy equivalence of the mass defect given by E equals mc squared.